Okay, section 6.5 is work and fluid forces. I don't do a whole lot of problems out of this section, so the homework shouldn't be too terribly bad. Let's talk about the units of work. First, we have joules. The joules is abbreviated with a capital J and pronounced joule, just like a diamond. It's named after the English physicist James Prescott Joule, and the definition for a joule is equal to 1 Newton times 1 meter. It's also can be called a Newton meter. In the British system, the unit of work is the foot-pound, and it's a unit frequently used by engineers. So you could use for the metric measure a joule, or for the English standard a foot-pound. The work done by a variable force f of x in the direction of the motion along the x-axis from x equals a to x equals b is going to be equal to the integral of that variable force f of x dx. Our first problem that we're going to look at is going to deal with Hooke's law. Hooke's law says that the force required to hold a stretched or compressed spring x units from its natural unstressed length is proportional to x. That means that there's going to be some sort of spring constant that we can find, where F is equal to kx. The constant K, measured in force units per length, is characteristic of the spring, called the force constant or spring constant of the spring. Hooke's law equation 3 gives good results as long as the force doesn't distort the metal in the spring. We assume that the forces in this section are too small to do that. That makes life a lot easier. So when a spring is at rest, it has some natural length. So if this is my spring at rest, if I were to compress that spring, let's say at rest it's a distance of 2 units. If I were to compress that spring 1 unit, then it would have a length of 1. So here I'm shrinking the spring, or I'm compressing the spring. So in example 1, we're told that it takes 1100 joules of work to stretch a spring from its natural length of 1 meter to a length of 2 meters. Oh, well, here I'm not compressing, I'll be stretching. So this is the natural state. And then if I stretch it, then I stretch it out to 2 meters. So we're told the amount of work that it takes. It takes 1100 joules. We're going to use this formula right here to first find that spring constant. So we start with the formula W is equal to the integral of f of x dx. We're told that the amount of work that we do is 1100 joules. We've stretched the spring a distance from where it is at rest 1 unit. So we've stretched this spring a distance of 1 unit. This is where it is at rest, and then we go out to 1, and that gives us a total length of 2. The force we're told is going to be K times X. Well, if I were to treat K as a constant here and integrate this function, I would have the equation 1100 equals K divided by 2x squared, and then we evaluate that from 0 to 1. We just start with the formula that we're given, plug in the information that we know, and then solve for what we don't know. So this is going to give us 1100 is equal to K over 2 times, evaluate our results here using the fundamental theorem of calculus by integrating this or evaluating this at x equals 1 minus x equals 0 squared. So we plugged in our upper bound minus plug in your lower bound, and that's going to give us 1. So we see that we have the equation 1100 equals K over 2, and we solve this equation for K by multiplying both sides by 2, and that gives us K is equal to 2200. That is the force constant of the spring, and that's what we were asked to find here. In example 2, we're told that it takes a force of 36,320 pounds to compress a coil spring assembly from its free height of 11 inches to its fully compressed height of 6 inches. Part A of this question asks, what is the assembly's force constant? The first thing we need to do is determine the distance that we compressed the spring. From the previous problem, we know that we have this equation. Work is equal to the integral of kx, where k is the force constant. In part A here, we're asked to find the assembly's force constant. So the first thing we do is we are going to find the distance that the spring was compressed. So if we start with an 11-inch spring, we compress it 5 inches. How I get that is 11 minus 6 is equal to 5. Then we know that the force is equal to K times X, where X is the distance that the spring was compressed. So we have 36,320 is equal to K times 5. To solve this equation for K, the force constant, we would just divide both sides of the equation by 5, and that gives us the force constant is going to be equal to, if we divide this by 5, we get 7,264, and that would be the spring assembly's force constant. In part B, we're asked how much work does it take to compress the assembly the first half inch and then the second half inch. These are two different problems, so we could call this part B, part 1. To compress this the first half inch, we would say that the amount of work done is going to be equal to the integral from 0 to a half, because we start out with the spring at its full length, and then we're compressing it 1/2 inch, and then times the force, the variable force, which is going to be 7,264x dx. When we evaluate this integral, we're going to get, so when we integrate this, we get 3,632x squared, and then we're going to evaluate that from 0 to 1/2. I'm just going to plug in my upper bound, because when I plug in my lower bound, I'm going to get 0. So this ends up giving us 3,632 times 1/2 squared. So that's going to be the same thing as 3,632 divided by 4, and that's going to give us 908. What are going to be the units for this problem? I have weight measured or force measured in pounds. I'm moving in distance of inches. This is going to be inch pounds. That's the amount of force required to compress the spring the first half inch. Now, part 2 of this part B asks us to find the amount of work done to compress it the next half inch. When you're compressing a spring, does it get easier or harder as you compress it more and more? It gets harder, so we would expect this to require more work, wouldn't we? So we set up our integral. What's going to change now is the bounds on the integral. The spring constant and the distance x is going to be the same as far as the integrand goes, but our bounds change. So when we started out, we compressed that spring 1/2 inch. So if we had an 11-inch spring, if this was 11 inches here, when I moved that compression, I went from rest, which is a state of 0, to a half. Now when I compress it another 1/2 inch, my bounds here are going to be from 1/2 to 1. That's the second 1/2 inch of compression. That's where that end point of the spring where it was at rest moved to. So we started out moving at rest at 0 to 1/2, and then for the second part of this question, our bounds are going to be from 1/2 to 1. Do you see where those numbers come from? So now let's evaluate our integral. That's going to give us 3,632x squared evaluated from 1/2 to 1. When we plug in our upper bound, it's going to be 3,632 times 1 squared minus 3,632 times 1/2 squared. Well, that's going to be 3,632 minus 908, because that's what we got when we evaluated this over here. And when we subtract these two numbers, what do we get? We get 2,724 inch pounds. It's important that you identify the units for these problems as well. For example 3, we're stepping away from the springs. In this problem, we're told that a mountain climber is about to haul up a 20-meter length of hanging rope. The question is, how much work will be done, or how much work will it take if the rope weighs 0.4 newtons per meter? So we have the formula, work is equal to the integral from A to B of some variable force, and we've got to figure out what that variable force is. We're told that the rope weighs 0.4 newtons per meter. You've got a rope hanging down. Let's say it's hanging off the side of a building. Okay, we've got a rope hanging down, and it's a 20-meter length of rope. We have the weight of the rope, and as we haul the rope in, is the rope going to get heavier or lighter? It's going to get lighter. So we can set up an integral for the work, and as we're hauling the rope in, we're going to haul in a length of rope that starts out at 0, where we've hauled in 0 amount of rope, all the way up to 20 meters of rope. The rope weighs 4/10 of a newton per meter of rope, as the length of the rope starts out at 20 when we've hauled in 0 amount of the rope minus X, and that's going to be going all the way up to 0. So 20 minus X is the amount of rope that we've hauled in, starting out at X equals 0. When X is equal to 5, we've hauled in 5 feet of rope, we end up with 15 meters of rope left hanging over the side of the building. Does that make sense? Do you see how we come up with this equation? It's the weight of the rope times the amount of the rope that's still left hanging as we haul in from 0 to 20 meters of rope. Since this variable here is X, we're going to integrate this problem with respect to X. So I can pull that constant out, and that's going to give us 4/10 times 20x minus 1/2 x squared. And we evaluate this from 0 to 20. Plugging in our upper bound, we're going to get 20 times 20 minus 1/2 times 20 squared minus 20 times 0 minus 1/2 times 0 squared. This is just using your fundamental theorem of calculus. Plug in your upper bound minus plug in your lower bound. And then taking care of the arithmetic, 20 squared is 400, minus half of 400 is 200, and then we get minus 0. And that's going to give us 0.4 times 200, which is 80. And what will be our units here? Our length of the rope was measured in meters. The weight was measured in newtons. This is going to be Newton meters, also known as joules. So it took 80 joules of work in order to haul up that rope. One more problem here, and that is our infamous leaky sandbag. This is a favored problem amongst mathematicians. So we're told that a bag of sand originally weighing 144 pounds was lifted at a constant rate. As it rose, sand also leaked out at a constant rate. The sand was half gone by the time the bag had been lifted to 18 feet. How much work was done lifting the sand this far? We're going to neglect the weight of the bag and the lifting equipment. We just want to know about the sand. We've got a crane out here on the edge of a building, and it's lifting this bag of sand, and the sand is leaking out of the bag as we're lifting it up. When the bag is on the ground, we haven't lifted it any. That bag weighs 144 pounds. We were told that. Once we lift that bag a distance of 18 feet, we've lost half of the sand. Well, half of 144 is 72. What that does is it gives us 2 points that we can then use to set up an equation, a linear equation for our variable force. We know that it's going to be a linear equation because things are moving at a constant rate and falling out of the bag at a constant rate, so that gives us a line. In order to write an equation of a line, we need 2 things. We need a point and we need a slope. Here's a point that happens to be my y-intercept. The next thing I got to do is find the slope. So this would be scratch work. I'll do it in green. The slope of that constant force is going to be, or that constant change, is going to be the change in the y values divided by the change in the x values, and that ends up giving us 72 over negative 18, which is negative 4. When I set up my integral for the work, my bounds are going to be from 0 to 18 because that's the distance that the bag has moved. The equation that I'm going to integrate over is the linear equation for the weight of the sand as that bag moves. So that's going to be 144 minus 4x. This is the slope and the y-intercept of the linear equation that represents that variable force as the bag of sand is lifted up the side of the building. Now let's integrate this. So that's going to give us 144x minus 2x squared from 0 to 18. Then using the fundamental theorem of calculus, we're going to plug in our upper bound minus plug in our lower bound, and that lower bound is just going to give us zeros here, so that's going to go to 0. And we have 144 times 18 minus 2 times 18 squared. When we plug this into our calculator, that's going to give us 1,944. What will be the units here? The units of distance that we're using are feet, and the weight is measured in pounds, so this would be 1,944 foot-pounds. And that wraps up section 6.5.